And we will cross now to Tibor. Tibor, tell us what stuff you want to talk about.
That's a nice segue. Well done. Okay, well, thanks everyone. I know this is meant to be a physics comedy night, but I'm not a very good comic, so I might have to do something serious. People do laugh at me often, but usually it's not because my jokes are funny. So I'm going to do something a little bit more serious. If you don't want to do any physics, any serious physics tonight, then just zone out for the next 8 or 9 minutes, okay? So what I'm going to talk, I'm going to address the question, is physics stuffed? In 1894, it really looked like physics was complete. Albert Michelson, he of the Michelson and Morley experiment, wrote that it seems probable that most of the grand underlying principles have been firmly established, and really all we have to do is fill in the 6th decimal place. But then somehow it changed. In 1900, Max Planck found black body radiation. In 1905, Einstein explained the photoelectric effect. In 15, he came up with a general theory of relativity, overturning Isaac Newton. In 1924, de Broglie came up with wave-particle duality, and then came quantum mechanics and the uncertainty principle and antimatter and quantum entanglement, and it just kept on going. So, in fact, everything changed after 1894. Albert Michelson could not have been more wrong. But then, in the early 1980s, everything changed again. We hit the blue screen. Lee Smolin, the father of string theory, wrote that in the early 1980s, things ground to a halt. He says physics has enjoyed 200 years of explosive growth, and we've discovered everything. Everything was going famously, and then it sort of fell in a hole. And he wasn't the only one to notice. Peter Voigt said string theory is not even wrong. It's not even a theory, so how can it possibly be even wrong? Philip Ball, an editor for Nature, wrote that we still don't have a quantum theory. Nobody understands anything. He thinks the whole thing is beyond weird. And Sabine Hossenfelder wrote that theoretical physicists used to explain what was observed. And now they try to explain what they can't explain, why they can't explain what was not observed. And they're not even good at that. She thinks physics has really gone astray, and she thinks it's rather lost in math. She may have a point. Today, things don't look so rosy. We can't find supersymmetric particles. They're not, the LHC hasn't turned them up. String theory can't be formalized or specified. We've got 5,000 different varieties of them, and none of them are any better than the other. General relativity doesn't square with quantum mechanics. Dark matter can't be found. Dark energy is even more unexplained, if it's possible to be more unexplained than unexplained. The standard model is incomplete. Vacuum energy is only out by a little bit. It's only out by about 120 zeros. Baryon asymmetry is unexplained. The foundations of quantum mechanics are utterly unresolved. Nobody understands it. And in fact, we still can't explain the double slit experiment. You might remember the double slit experiment. It's the one that looks like this. When you fire electrons through a double slit, you get this diffraction pattern, even if you fire the electrons through one at a time. And no one can explain it. Here's Jim Al-Khalili at the Royal Institution.
If you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
And there is. So if you think of a solution, please write to Jim Al-Khalili. I've got his email address, so contact me and I'll put you in touch, and you can go and collect your Nobel Prize. So the question is physics stuffed? Have we really stuffed things up? Now the answer is no, I don't think so. I think what happened is that in around 1900, or perhaps as early as about 1856, when James Clerk Maxwell developed his electromagnetic field theory, physics went on a detour. It changed its focus. Instead of describing the physical world and how the physical world is, it turned to describing how the physical world appears to be. And that's not the same thing. Physicists found new toys to play with, not physical things, but imaginary mathematical things like symmetries and invariances. And they move from playing in physical space to playing in some imaginary parameter space. Basically, physics just isn't physical anymore. And I'd like to demonstrate this point with a couple of demos that I found from Harvard University. Here's one. Okay, these are Chladni plates named after Ernst Chladni, or Schladni, as I found out his name is, a German physicist and musician. Obviously, he played the violin. The patterns that you can see, they get incredibly complicated. The higher the frequency of the resonance of the plate, the more complex the pattern. Now, that's fine, but the important point is this. In 3 dimensions, these patterns are called spherical harmonics, and they describe exactly the structure of electron orbitals around atomic nuclei, which look like this. So electron orbitals around nuclei are nodes in spherical harmonics. They're minima in standing waves. There's no physical electron particle whizzing around the atom. Electrons are not particles at all. They're just the name that we give to these observable patterns. Here's another example. 15 pendulums swinging independently, as you will see. Watch the pattern, it's very interesting. Okay, and it goes on. The complicated wave patterns that you saw weren't actually there, of course. They were just an apparition created by the 15 pendulums swinging in the background. Again, the description of wave packets in quantum mechanics is the same as the mathematical description of this imaginary wave. So again, there's no actual wave packet objects or particles in quantum mechanics. Jeremy Butterfield from Cambridge University explained, there are no particles anywhere in quantum mechanics. The standard model is not made of particles. Quantum mechanics is also about appearances. They're about the waves that you see and not about what's actually going on behind the scenes. And we know this, okay? Niels Bohr famously said, physics is not about describing how nature is. Physics is about what we can say about nature. It's about what we can see. Ilya Prigogine, a chemist, got a Nobel Prize in, when was it, 1977. He says, seeing the world from the outside is not the object of physics. Rather, it is to describe the physical world as it appears to us. So really, we're not describing physics. We're not describing the physical world. We're describing how it appears. And this makes a difference. So to me, it seems like there's nothing physical about contemporary physics. Physics isn't stuff. It's not even about stuff. There's no stuff in contemporary physics, in particular in quantum mechanics, which is more like describing or predicting appearances than it is about describing or understanding the physical world. And there's a problem with this. Appearances are not governed by dynamical physical laws. They're orthogonal to the laws. So the more we focus on appearances, the further away we get from describing what's really going on. And here's an example of that. In the Mandelbrot set, I'm sure you're all familiar with it, the more precisely we describe the circles, spirals, and seahorse tails, the further away we are from discovering the simple dynamic process that generates the entire pattern, which is just that one-line equation. And so it is in the case of the standard model, for example. The standard model of particles, you can write down the Lagrangian, which looks something like this, But this is only the abbreviated version. The full version actually looks like that, and that's still not complete because it hasn't included dark matter, dark energy, and gravity. We're making it more and more and more complicated. And I think we're getting further and further away from understanding what's actually going on behind the scenes. So this leads me to ask, and I'll leave you with this question, might it be the case that physics is looking at things the wrong way? Let me end by thanking Phil, Fred Osman, and of course, you. Thank you very much.
Fascinating stuff. Erin, thank you. My mind is blown. This makes me feel better about the amount of biology that nobody knows. It's interesting to me, as a scientist, I think a lot of people think you know stuff, and a lot of people come to me and say, do you know stuff? And I feel like I know much more. My whole history of science has been about learning what I didn't know.
Sad but true.
It's kind of like the expanding universe. The more I learn, the more the boundaries disappear over the horizon. And the worst I got. And yes, they have seen the McDonald's sign. David Dawes from Melbourne, he's seen it. Put your finger on it.
Yeah,
that's just
there.
Around there. Yep, that's it.
Just there.
Beautiful. All right. Is William of Ockham right? There's a question for you.
A very good question. Albert Einstein had something to say about that. He said we should make our theories as simple as possible, but no simpler. You don't want to oversimplify things because then you start throwing out the baby with the bathwater. So I think we're not looking at the right thing, which is why it's getting increasingly complicated. And yes, I think Ockham is right. I think the world is not clever enough to be as complicated as all that mathematics. Elementary particles don't walk around with calculators doing Fourier analysis trying to work out where they have to go. We're somehow thinking that it's far too complicated, far more complicated than it really is. So I think we just have got the wrong perspective on things. And one day, Mr. Zweigsteiner, he's the one that comes after Einstein, Mr. Zweigsteiner will come along and turn the whole thing upside down and say, yeah, you need a new theory. Here, look at it this way. That may happen in this century.
And everyone will say you've got two rocks in your head.
Yeah.
Which is what Zweigsteiner stands for.
Exactly. Yes.
Here's an interesting comment. Very compelling. I can't help but think this is akin to observations about how news presentation has changed. Rather than presenting it and letting us form opinions, it's presented with opinions now. There you go. It is kind of quantum mechanical, but I think it's interesting in the science journalism world, and perhaps from scientists as well, realizing that they cannot be objective. Although we strive for it, you are always making judgments about what you include in a story, what you don't include in a story, what you choose to measure, what you don't choose to measure. These are all subjective choices. And so the dream of an objective science, an objective individual, is very difficult to argue, but somehow the collective knowledge arises, which is actually a reflection of how the universe really is. So it's quite a remarkable thing, I think, the way science works and how we have, as a group, managed to form something that is greater than the parts, the individual parts.
Yeah, the problem with the science popular press, of course, is that their number one mission statement is to sell their journals and magazines and books. And it's not about scientific accuracy. It's more about whizzing up the story and making it sound sexy so that people buy their product. And so quite a lot of the good science, which could be communicated, gets distorted by the media on the way out. So we've got several problems. One of them, scientists are not very good at communicating their science. Secondly, the media then go and screw it up. So I don't blame the general public for not understanding what physicists are doing, even less than we physicists understand it.
On that note, I have a little clip to play. So I might just, I'll come back to it because there is another question for you. What's the state of string theory research? Has it effectively been abandoned?
Almost. There are still only just a handful of people working on it. Brian Greene is one who loves it to death. But people like Lee Smolin, he actually gave up on it. He publicly declared, and he does so in that book, he says, I'm giving up on string theory. He's now at the Perimeter Institute working on something else. So generally, I think string theory is largely dead in the water. It's been replaced by things like loop quantum gravity and quantum gravity of other sorts. And there's other theories around which kind of try to mimic or try to reproduce what string theory is trying to do. But string theory, I think, as such, has been largely abandoned. I'm happy to be corrected if anyone knows, anyone who's furiously working on it, but I haven't heard of anyone.
Yes. Actually, I'm going to throw to Tony here, whose presentation a couple of years ago was basically the mathematical derivation from group theory of how particles come to be from a mathematical point of view, particularly as Tibor kind of mentioned that comment about there's no such thing as particles. What's your take on that, Tony?
I think that quantum mechanics is studying the act of observation, act of perception. It's moved away from thinking there's a universe out there and that there's us here. It's us understanding how we see the universe. That's very clear. And I agree, there are no particles in physics. They're all group representations, mate.
And what do you know?
Let's get together over a bottle of wine and I'll try and explain what I mean by that comment, if you like.
I'm in.
And right on cue, here comes Schrodinger's cat. He's just woken up and he's hungry. Have you got anything to say? Clearly not. All right. Now, don't you walk on the keyboard. He did a Google search yesterday for M comma while I wasn't looking. I don't know what mathematical representation M comma is. Perhaps you'd like to share, Tony? All right. Enough on that note. I am going to throw back to an excerpt from an earlier show back in the day when we could be in pubs from Canberra live show Stir Fried Science in April this year. So there we go. The whole question of should we make astronomy more sexy than it already is? There you go. Now, there's actually a question in the Q&A. What have we got here? Open that up. Is it possible that physics and indeed education has been too formalized? Students are being trained to think one way and there is no scope for imagination. Oh, who wants to take that one on? I certainly have opinions about it. Tibor, do you have an opinion first?
Yes, I do. I think that it's correct. I think that's a fair observation. As I see it, the education system altogether now, that includes universities, is focusing on teaching people what they need to know and what to think, rather than teaching them how to think. And that's true even in the philosophy department at Sydney University, I'm sorry to say. So yes, there's no room for criticism. It's really interesting. I have some thoughts about how we might go about fixing up some of this physics stuff. And every time I try and talk to a physicist about it, they very quickly conclude that I'm a crank. Basically, they're not interested in anything that doesn't fit in with their quantum field theories and their everything else that they're working on. So no, they're intolerant of novel ideas. They've got too much of an investment in their careers, maintaining the status quo, pushing the science which everybody is working on. And you really get into trouble if you step off that thin line and you go off on a tangent and try and come up with something new. So new ideas and radical thinking outside the box is not encouraged in physics, again, as I see the industry.
That's an interesting take. I mean, my 2 cents worth is that there is so much that you need to learn and so much structure that you need that's been built up, that you have to learn that first. And once you already know the orthodoxy, then you can take it. I mean, the problem, I've been at the front line of this when I was at Sydney Uni. I used to take the calls from people who'd ring me and say, I've proved Einstein wrong. It's like, oh, right. Okay. And how so? Oh, it was E equals M squared over C cubed. And I'm like, okay. why? Well, can you just help me with the maths? It's like, no, I can't actually, because the maths is where it's at, and kind of that's where, from what I'm hearing from you though, is that you think that there might be an alternate maths that's maybe, got a much simpler structure to it. But I think that's got to come from somebody who already knows the ins and outs of things very well before we can, you can't just come out of nowhere. So you've got to have the mixture of the rigorous built up knowledge and then the ability to play and be creative within that.
Okay,
it's
so
very difficult.
Here's a trick question for you, Phil. We've got an m in the equation E equals mc squared. I know it's not quite the right equation, but it's close. Yeah. And we also have an equation m in kinetic energy is a half mv squared, for example. Did you know that the m in those two equations does not mean the same thing, and they don't refer to the same thing? They're different m's. Mass is not the same in the different theories because masses don't behave the same way in the different theories. So these are the kind of subtle differences that need to be thought about at the bottom of physics, which I think are now being overlooked or have been overlooked for the last 100 years or so. That's why we have trouble unifying quantum mechanics with relativity, for example. Because even the concepts that we are describing in our equations, sure, the maths is great, but they're not referring to the same entities. So there are some interesting subtle problems there, which, okay, the person who comes to you and says it's E equals m squared over c cubed might not have got a handle on. But that doesn't mean that there aren't some really out of left field questions that somehow are begging to be asked.
And that's why you, as my friend likes to call it, as a heterodox,
yeah.
is because you have the skill to note that difference between the two m's in the different equations. That's that gives you something to leverage on.
Yeah, I was just going to say, having taught at universities and also high schools and stuff, I certainly like to think there is a lot of scope for creativity by asking the question why. I mean, the most basic question in science is I do not know, and I'm questioning to find out why. And physicists or scientists love being proved wrong because then they can correct their mistakes. So I certainly like to think that there is a lot of creativity encouraged in the students. And if you're teaching science at all, physics or chemistry, you should be connecting it to a whole lot of other areas in the mathematics, into everyday life. And by doing that, you get students to think about what they're doing.
This is such an interesting debate, but I'm going to call it. We've got to move on because we are now going to go to Russia and look at spy planes.